6. Consider the function f of x equal to this, whose first and second derivatives are this. We have the first derivative, we have the second derivative. Give the domain of the function, that's the A part. B, determine the intervals on which f of x is increasing or decreasing. We have the C part, find the local extrema. And D, determine the interval on which f of x is concave up or concave down. Let's look at the solution to this question. The first one, the A part, the domain f of x. If you check your f of x, the domain for A is all real value except plus or minus 1. If you put 1 there, it will be 0, and anything by 0, that's infinity. So all real value except this value. The domain, that's the domain. The domain is not equal to plus or minus 1. Determine the intervals on which f of x is increasing or decreasing. We'll be given the first derivative. Just equate that first derivative to 0. If you do that, is your first derivative. If you equate it to 0, it's going to give you x equal to what? Equal to 0. Just equate the whole fraction to 0. So we only have, this is a critical value. The critical point is what? Critical point is, this may not be enough for us to analyze our intervals of increasing and decreasing. So what we're going to do, we're going to find the first differential of that function. We're going to equate it to infinity. What is the meaning of that? The meaning of that is your denominator equated to what? Equated to 0. That's the meaning of the first differential equal to undefined. Okay? And this will give you x equal to what? Plus or minus 1. But this value is not a critical point, because this value is not in the domain. We are going to use it to analyze our interval of increasing and decreasing. So we're going to have the table, our test points. So the interval, as we all know from the domain is all real numbers except these plus or minus 1. So we're going to start from negative infinity. We have we're going to use this one, minus 1. Okay, and followed by minus 1, comma 0. So this one will be 0, comma 1, finally 1, comma infinity. So we can take a test point here between these negative infinity and minus 1. We can take minus 2. Here we can take 0. Here we can take 2. Between 0 and 1, we can take 0. Here we can take minus 0.5. Here we can take 0.5. Here we can take 2. So if you substitute this one there, this will be positive. So your first differential, put the value there, that will be positive. You just want to know whether it's negative or positive. That's what we call the sign of f prime. This negative, put it there also. It will give you positive also. This 0.5, put it there, and that will give you negative value. And for the 2 also, that's negative also. The nature of f of x here is increasing here. This one is also increasing. This one is decreasing. This one is also what? Decreasing. So I can say f of x is increasing this interval, minus infinity, minus 1, and minus 1, comma 0. And f of x is decreasing on 0, comma 1, 1, comma infinity. So that's on the increasing and decreasing, which is very simple. Just for you to play with your critical value. That value is not enough. You just have one value. Okay, so we have to use the first differential as undefined, and we're able to get some point there. Okay, actually it's not the critical point, but we use it in interpreting our increasing and decreasing. The C part, find the local extrema. What that one is meaning that is there any minimum point there? Is there any maximum points? That's what I want to find. And we're going to make judgment based on what we have here. You can see it's increasing from this boundary. It's increasing here. Okay, it's increasing, and at 0, there is a change in the sign. It started decreasing at point 0. Started decreasing. That means x equal to 0 is going to be a minimum value. X equal to 0. F of x equal to 0. If you put in your equation, can also check f of 1. So if you look at it, f of x has a local maximum at s equal to 0. And you can see the value here is increasing. Okay. And then at the point of 0, that's why it started decreasing. Then once you go to the d part, determine the interval on which f of x is concave up or concave down. For concavity, we use the second differential. Okay, we equate to 0. And if you do that, it's going to give us also x is equal to what? X is equal to 0. Then at the same time also, we can also get more points. The second differential is undefined. If it's equal to infinity, that means the denominator will be equal to 0. And that will give us plus or minus 1. Okay, but this is not in the domain, but we're going to use it for our table to get the concavity. So we're going to have minus infinity, and this is minus 1, comma what? Comma 1, and then 1, infinity. This second differential equal to 0, giving us 0 is an inflection point. Whenever the second differential equal to 0, that point is an inflection point. Okay, so this is all we have now. Can we get the text value between here? We can pick minus 2. We can take 0 here. We can take 2 here. Okay, then we have the sign of second differential, and then the nature of concavity. So if you put minus 2 in the second differential, it's going to give you positive here. It's going to give you negative here. For 2, it's going to give you positive. So in that case now, we have here, since it's positive, it's going to be concave up. This one is down, it's negative, that's concave down. When positive, concave up. When your second differential sign is positive, that's it's going to be concave up. When it's negative, it's going to be concave down. Okay, so it's concave up on this interval as minus infinity, comma minus 1, 1, comma infinity. Concave down on minus 1, comma 1. So that one has been shown. In addition to the question which I didn't write initially, is E part, find the vertical and horizontal asymptotes, and then sketch the graph. Okay, so in finding the vertical asymptotes, what we are going to do is to equate your second differential, the denominator, equate to 0. So whatever value you have there, that is your vertical asymptotes. Okay, so we have plus or minus 1 in that case. So we're going to take the limits of the function with x tend to 1, negative infinity, and do the same thing also of this function as x tend to 1 to the right. This one 1 to the left, 1 to the right, 1 plus. If you do that also, it's going to give you plus or minus infinity. For x equal to minus 1, let's do the same thing also. Limit of this function x tend to minus 1 to the left, that will be minus infinity. Also limit as x tend to minus 1 to minus 1 plus of the function, that will be equal to what? Plus infinity. So that's how to show for your vertical asymptotes, give you negative infinity, plus infinity. Then the last one is the horizontal asymptotes. For the horizontal asymptotes, just take the limit of the function x2 minus 1 as x tend to plus or minus infinity. This one, the highest power here is x to the power 2. So divide each term by x to the power 2. So this will be 1 plus 1 over x squared all over 1 minus 1 over x squared. So by the time you do that, it's going to give you what? It's going to give you 1. So in getting your horizontal asymptotes, you use that function, and then it's going to tend to plus or minus infinity, and then you solve it. So in most cases, you don't even do direct substitution. By the time you use your algebra, you're going to get the value. So that's that on the vertical and horizontal asymptotes. So the next thing to do now is to sketch the graph. Yeah, in sketching the graph, we'll need the concavity, the nature of the concave up, concave down. Okay, you can realize that at minus 1, it's concave up. It's concave up here, but at minus 1, that is what is moving down. It's concave down. So this is my y-axis. This is my x-axis. So let me just indicate this one is 1. This is a minus 1. There is a vertical asymptote at s equal to plus or minus 1. So I'm going to indicate that in this place. So that's my vertical asymptote. It's just a straight line. S equal to 1. You draw a straight line. S equal to minus 1. You draw a straight line. Okay, this is your origin. Then again, we have the horizontal asymptotes at s equal to what? At s equal to 1. So this is my 1. Draw a straight line also for horizontal asymptotes. Y equal to 1. Draw a straight line. Then there is a concavity at minus 1. It's not going to touch the minus 1. It's going to go down like that. Same also here. It's going to go down. It's not going to touch the display. It's going to go down like that. So that's a concavity at s equal to 1. Then in this case also, you just draw your graph. The same thing also you do here. Okay, so that's that on these aspects. On the playlist, I've really explained this in depth. So please endeavor to check the playlist. And the thing is that you need to keep practicing. The more you practice, the better you become. Keep practicing. It's go beyond just watching the video. You need to take your journal. Okay, take your pen, take your paper, and begin to work along with the speaker. That's very important. Okay, on the final note, don't forget to click on the watermarks on the video and subscribe. Click on like button and begin to type your comments. Finally, share the links of this video on all your social media platforms.